should be very similar because each time step you making action and the state is kind of different, changing, but even though you take the action, state slightly change, right? So the data is very similar. But when you get the mini batch from the replay memory, we just randomly get the data from the replay memory. So we can reduce the correlation of the data, and then we can in a better way to train a neural network model. So the algorithm, just get the data. It's exactly what I'm told. Get the data, push the data to the replay memory, and then we get the mini batch, and then we train the model. And then, so the point is how we train the model. We just focus on the big picture of the skill learning. I know we should know the mathematical detail, but in this video, I just want to focus on the big picture of the thing. So the big picture is something like this. You can see in the slide. So you have a neural network model, and then, for example, the state is an image game screen of the Space Invader. So you just put this image to the neural network, and the neural network are going to produce numbers, but the number is not the single number, it's multiple numbers for each action. So, for example, in the Space Invaders case, you have 6-dimensional actions, which is you want to kill the enemy, or you want to move at and also fire, or you just do nothing. And then for each action, you have a value, which is a Q value. So the Q value is so long story short, it's a number that you expect it to have within the expected reward you're going to have within the one episode. So simply saying, if you have high number in this Q value, you should do that because you can get more higher scores within the game. So in this case, just example, we have a sequence of numbers, and we realize the Q value of the left action has the highest value. So which means if in this state, if you take the left action, you can have a higher scores. So why don't you just do the left action? So in the Q learning, you produce multiple numbers, and you take the maximum, and then you can decide action. So in this case, moving left is a good action. So that's the idea. So the point is how we are going to estimate those Q values. We can think of something similar to the regression. So why the regression model can produce numbers? It is because you have a true value, and then you have estimated value. So we want to take the difference of true and predicted, and then try to minimize this difference, which is called root mean square error loss function. So we are going to do something similar here. So we prepare a target data, which is shown in this equation, and then we are going to, the other side, we are going to prepare the estimate value, which is, you can make that estimate value by this, and then the point is, you just take a difference, and then you take the square of it, and then you take the mean, which is the mean square error, which is going to be the loss function. And then, because we're using the neural network, why don't we just differentiate the loss function, and then we are going to do the gradient descent, which means, so here theta is a parameter of the neural network. So we have current parameter, and then you have alpha step size multiplied by the gradient of the loss function, and then we just do this many times, and then we can optimize the parameter of the neural network, and then the neural network can produce a nice Q value numbers to decide the actions. So that's it for the major concept in the DQN. So why don't we just take a look at the implementation? So here, I'm not actually using the Space Invaders. We're using the carpool environment. So I chose carport environment because carport is a kind of base environment for reinforcement learning researchers. So even though someone uh, develop a new idea of reinforcement learning algorithm, we want to test first in the simple environment, the carport, and then test it, what's happening. So it's good to know about this environment, because if you read the paper, you're going to see this environment so many times. So carport is a four-dimensional state. So carport is something, you have a car and you have a pole, and then you want to move the car to try to balance this pole. So you have four dimensions, 2 dimension for car and 2 dimension for pole. And then the action is just two, we just move right or left. Maybe that's opposite to the camera, but and then you can collect the reward, and every time say you can get one. So and then this environment going to end if the car is moving away from the center, or the pole is, the angle became bigger, so that means kind of fall down. So our objective is to want to maximize this reward, which means you want to correct as one so many times, which means you have to balance longer, and then you can get more reward. So that's the objective. So you have a video which is in the real life setting. So if you see that, it's kind of very fascinating. And then we have code in a Python program and also Jupyter Notebook. So if you go to the GitHub, which is shown here, you can just pull those code. And especially the Jupyter Notebook is intended to run in the Google Colab. So you don't have to prepare your local environment. You just download the notebook, and then you go to the Google Colab and upload the notebook to the Google Colab to run it. So you have a setup. You have to run those two lines, because the carport is a data structure which you can get from the gym package, but gym package sometimes doesn't work in the Google Colab. So you have to have these two lines and some other lines to make it work in a Google Colab. So that's the setup, and then you have many parameters because this is because you're using a neural network, and also reinforcement learning tends to have many hyperparameters. You can take a look at that later. So you have a model. This is it's a neural network to process the state and output the actions. So here we using the two hidden layers. Each hidden layer has a 256 filter. So what you can notice is, hey Yuki, you're just using the two hidden layers, and then you just still you're calling the deep Q network. Yes, that's a good point. It's actually not that deep. For the experience replay memory, it's better to have a data structure. So here we're using the class, and in the experience memory, you can we have a buffer. So in buffer we add in those data in the list, and then you have a store method, so you can put the data inside this buffer. And then we have several helper functions, for example, get action, which is an implementation of Epsilon greedy algorithm. Do you still remember the algorithm that I just talk about? The experience replay. Epsilon greedy algorithm. So Epsilon is a threshold, and then we generate the random number. And then, for example, if the Epsilon is a 0.1, and then random this function going to also produce between 0 and 1, and Epsilon is also between 0 and 1. And let's say the Epsilon is 0.1, and if the random value is 0.05, because it's below the threshold, so we are going to take the random action. But occasionally, if we have a random number, for example 0.7, which is higher than the threshold, so we are going to listen to the model. You also have the update model, which is implementation of the Q-learning. So we get the mini batch from the experience replay, and then we get the target value, and then we have the estimate value, and then we are going to take the difference, square it, and then